All right, we are recording now. So, just a statement of the problem. Ball is to be shot from ground level with a certain speed. Okay. So the figure shows the range R. So, okay, I guess V naught is some, given speed. The figure shows the range R it will have versus launch angle. Okay. And it just looks kind of like a parabola. The value of theta naught determines the flight time. So then T max is the maximum flight time. And it's asking for least speed that it'll have if theta not chosen such that t is equal to like 0.4 t max, let's say. Okay, so just a couple of things based on the graph, or based on the initial statement of the problem. So t max, it should be pretty intuitive that t max is gonna be when theta is equal to 90 degrees. Do you buy this? Because this is basically saying if it's a cannon, gosh, how do you draw a cannon? It's basically saying it's launching the ball straight up and coming back down. That's going to take the longest time, as opposed to launching it out of any other angle where it has less initial horizontal vertical velocity. Does this seem believable?
Bro, are you sharing screen?
I am not sharing my screen. My bad. Let me fix that. Let me fix that. Screen share. Okay, how about that?
Got it.
Got it? Okay. So, all right, let's start that again. So I just drew the, what do you call it, the parabola. And I said, okay, here's Tmax. They tell us that, they just give us the concept of Tmax. And I'm saying to you that Tmax is basically when theta is equal to 90 degrees. Do you buy that? Because if you shoot the thing like straight up, it's going to take a lot more time than if you just shoot it like a couple degrees up, right?
Right.
And intuitively, it'll take more time than any other angle. And the reason is basically because shooting it straight up maximizes, V naught in the y direction. So it sort of takes the acceleration, it sort of takes longer for the acceleration to eat away all the positive velocity it has and then to bring it back down. That's the idea. I think this is obvious enough to not require a proof, but I mean, we can prove it if need be later, as maybe like an appendix. But the other thing that is probably worth noting is that the R at the max is going to be when theta is equal to 45 degrees. Does that seem believable? I can also prove this at the end, but I think it should be kind of reasonably intuitive that the absolute furthest you can shoot the thing is when it's exactly sort of halfway between 0 and 90. Right?
Yep.
Because if you're shooting it directly upwards or directly to the right, the travel distance, horizontal travel distance, is going to be a big fat 0 because it's just going to plop down. And it sort of stands to reason, you can prove it using calculus, but like the sort of midway point is sort of the Goldilocks zone of making it as far as possible. So that's sort of R max when theta is equal to 45 degrees. So far, so good?
So far, so good.
Okay, so that's just sort of the setup. So one of the things to do is let's start by finding what Tmax is in terms of our other variables. And like I said earlier, Tmax is when you shoot directly straight upwards. By the way, for the person joining us, we are recording. I'm just doing an explanation of the problem where you're trying to find the least speed. Oh, and the other comment I should have mentioned is that the least speed on some path, right? If you're shooting like a parabolic path, well, that's just the speed at the peak of the height, right? Because the horizontal velocity is always going to be there. Just remember that horizontal and vertical velocities are kind of independent of each other. So the point where you can have the least speed is basically when there's no vertical velocity. Does that make sense?
Right.
Right.
Yeah.
Because the horizontal velocity isn't being impacted by any force. It's always going to be there. So, if you, you have to take that, you have to account for that. But apart from that, we can try to look at the point where the vertical velocity disappears to find the least speed. Anyways, I would say step one is probably to find what Tmax is. And that's not so bad. Remember, we said that Tmax is when theta is equal to 90. So we just sort of change that into our equation for delta y. So this is when delta y is equal to 0, and that's just equal to v naught. Okay, we can say sine of 90 if we want to, but that's times t max minus 1/2 g t max squared. And if we solve this, well, that theta sine of 90 is just 1. So that's basically saying v naught t max is equal to 1/2 g t max squared. And doing a tiny bit of cancellation here, it looks like 2 v naught over g is equal to t max. So far, so good?
Yep.
Okay. So then it looks to me like the t of the second launch, I don't know, what do you want to call it, t new or something, is equal to 0.4 2 v naught over g. This will become important in a little while, but there's still a little bit more groundwork to be laid. What else? God,
Wait,
my notes
I'm
are...
lost. How'd you
What's
get
up?
T new?
What's up?
How'd you get T new? What is T new? How'd you get T new?
Remember the problem was just asking us what is the least speed the ball will have during its flight if theta naught is chosen such that the flight time is like 0.4 t max. So I'm just saying that this is the, it's sort of saying we're choosing a new flight, right? We're contriving a second launch so that the t of the new flight is 0.4 times t max.
Okay.
Right? So this is just what the problem is asking us. If we were to do another launch chosen for t to equal 0.4 t max, I'm just plugging this in for t max. You see that?
Yeah.
Just plugging that right in. Okay. Oh gosh, I have some of my notes. I don't have all of my notes. Where did they go? Okay, I'm just gonna try to wing it. Okay, so then t is equal to delta x. What else can we say about this? Okay, so the question was asking us what is the least speed the ball will have during its flight. Can v naught be found? Okay, let's next thing, let's find v naught. Next step is find what v naught is from the graph. Yeah? So the max distance from the graph looks to be about, I don't know, 250 or so. And again, just to emphasize, that's just basically looking at the tip of the graph and seeing that, oh, that looks like 250. And remember, the maximum is when theta is equal to 45 degrees. But maybe it's worthwhile doing a little bit of a quick proof for this. So delta x is equal to v naught cosine theta t. This is just general. This is for any theta, right? And delta y is equal to v naught sine theta t. So right now, I'm just going to do a quick proof. X is max when theta is equal to 45. But that's 1/2 gt squared. So we get that, I'm just going to quickly skip the math a little bit. T is equal to, I think, v naught sine theta over g. Is there a factor of 2 here? So I'm saying that when I'm looking for the time when it hits 0 in order to try to find t to get the range of the total flight. So v naught sine theta t is equal to 1/2 gt squared. I don't know why I canceled out a 2 in my notes. That's very odd. What is this? V naught sine theta t is equal to 1/2 gt squared. So the squares cancel out. So we get that t is equal to 2 v naught sine theta over g. Okay. And then at this point, we can just plug this right back in here to get delta x is equal to v naught squared 2 sine theta cos theta over g, I believe. Does that seem right? And then v naught squared 2 sine. V naught cosine theta. Sorry, I'm just double checking 2 sine theta g. Yeah, and this is just equal to V naught squared, and using the trig identity, sine of 2 theta over g. And then to find the maximum, we just do dx dt is equal to V naught squared cosine 2 theta g times 2, and set that equal to 0. And this is equal to 0 when theta is equal to 45 degrees. So that's just a quick, maybe not so quick proof that theta is maximized at 45 degrees. But the entire point of this, the entire point of this was to prove to us that we could just find the max range by just looking right there. Yeah, sorry about the very lengthy diversion. But this means that, okay, now we have we can figure out a way to find V naught, because what did we say? By plugging everything in, we said that delta x is equal to V naught squared sine of 2 theta over g. And we should be able to just plug this value right in. We should be able to plug that 250 right in, and then get that, what is this, like 250 is equal to V naught squared. So then theta is equal to 45, so sine of 2 theta just disappears, and that's over g. I'm a little bit worried that I dropped a factor of 2 at some point through this process. Like, in my notes, I have a factor of 2 here that goes away. And I would advise that when you work this problem out for yourself, you double check it thoroughly. But yeah, so this expression right here, delta x is equal to V naught squared sine 2 theta over g. I just got that by solving for t using the y equation and plugging that right in. So do that for yourself and double check my math there to make sure you're not off by a factor of 2. But the whole point is that we can find V naught at this point. Yeah, we can find V naught. And once we have V naught, I think we are very close to being done, actually. Because once we have, an honest to goodness expression for V naught, which at this point is literally just a number, right? Because 250 divided by g, take the square root of that. V naught is just a number. Well, at this point, we can just set up our kinematic equations again. We can find delta x is equal to cosine theta V naught. At this point, this is known. And times 4 2 V naught over g. Right? So this is basically saying, okay, for our new launch where t is equal to like 0.4 t max, we are trying to find we're trying to find if we can find theta, we are done, because the min speed is equal to, remember we said that the minimum speed is just equal to the horizontal velocity, because the minimum speed is going to be the velocity at the peak with no y component, only x component. So that's equal to v horizontal, which is equal to v naught cos theta. So at this point, if we can just figure out what theta ought to be, we are done. And at this point, delta y. Yeah, okay. So at this point, delta y is going to be equal to sine theta, v naught times, I'm just going to use this t, so it's 0.4 t max, minus 1 half g t 0.4 t max squared is equal to 0. So what do we not know? I'm pretty sure at this point this equation is just solvable, right? This equation is saying the change in y from launch to landing is going to be 0. And it's saying, okay, so your initial velocity in the y direction is just sine theta times v naught. And remember, we know v naught. At this point, we know t max. And yeah, given all that information, we ought to just be able to solve for sine theta. Solve for sine theta. And once we have sine theta, we can find cos theta is just equal to 1 minus sine theta squared. And take the square root of that, right? And at that point, once we have cos theta, we can just plug it in over here, and we already know v naught. So at that point, we should be done. This proof was, this problem was a little bit messier than usual, and maybe I should have thought about the presentation a little bit beforehand, but am I making sense, or should I go back and readdress some stuff? What is this looking like right now?
I think you're good. It made sense along
made
the way.
sense?
We should have real values most of these points. So I mean, I didn't get lost.
Okay, good. Okay, sometimes when students aren't too talkative, sometimes I'm worried that we lost them along the way. But with this problem, I would just really double check. When I'm doing this, I'm not being super careful in my calculations in areas that don't matter too much. But because you're putting this into a actual like WebAssign or something, you got to make sure your factors of 2 and all are correct, right? So what I would do is I would go in there and make sure that this expression for delta x is actually correct, because we're using this expression to find. We're using this expression to plug in 250 to find out what v naught actually is. And I'm kind of worried I dropped a factor of 2 somewhere along the way. But apart from that, I hope that this makes some sense. For those of us just joining, I was recording this, so I'll put a recording on YouTube. But yeah, I mean, when I do these problems, the intention is not to solve everything for the student. And if I drop a factor of 2 or root 2 along the way, I think it's pretty fair game to tell the student to make sure to double check the work and actually solve it out for yourself so that you understand what's being done. But I think I'll end the recording right there unless there are any other specific questions.
I had a question.
Sure.
The delta x proof. Why did we go through that whole proof?
I needed to justify this thing right here. Y theta was equal to 45.
Okay.
This little segue was sort of for 2 purposes: justifying why theta is equal to 45 reaches the maximum range, and also, just as a side note, it also let us figure out the relationship between. It also let us put t in terms of v naught, so that we could plug this t back in here to get this equation. You see that?
Yeah.
And yeah, looking at it right now, I think I egregiously just dropped a factor of 2, right? Because there's a 2 here, and 2 v naught sine theta g times v naught cosine theta. Yeah, I think there would have to be a factor of 2 over there. But that's for you all to double check. I will leave that to you. I don't know. This was not my most careful calculation. There's some factors of 2 all over the place. You gotta look out for. Okay.
Will do.
All right.
Thanks, tutor.
Sure thing.